Hello everyone. In this experiment, we're gonna see how a dynamic absorber works. What we do have here is a beam clamped at both ends, and we do have another mass attached to it just tightly. We have this mass attached to the original mass here. So meaning that we have a single mass, and so meaning that this system has a single degree of freedom, and so it does have only one natural frequency. Assume that this system is being excited by in a real system, it's being excited by an unbalanced system, which by chance the natural frequency, the excitation frequency of that system coincides with the natural frequency of your system. So what's going to happen? Of course, resonance. To avoid resonance and to avoid possible failure of the system, so we need to do something. So the easiest thing that we can do is just to add an extra mass to your system. So what we do here is just we unscrew this mass here, and so basically this mass is independent of the original system. So now we do have two independent systems, or two independent coordinate systems, or two independent masses. So now this system has two natural frequencies, which these two natural frequencies are different or off from the original natural frequency of the system. So I'll just pass the rest to my esteemed colleague Stefano to just present this interesting observation and this interesting demonstration to you. Thank you.
Hello everyone. So as Hamad said, this is called the dynamic absorber, and we have a rigid beam, and to excite this beam we are giving power to this engine, and this engine is going to work as an unbalanced mass, and these two gears are going to compensate horizontal forces and apply only vertical forces to the beam. The beam has this mass attached, so right now the screw is tied, so it's working as a single degree of freedom system. This mass can't move independently from the beam. That means that it's going to have, so it has 1 degree of freedom, it translates in one natural frequency and in one mode of vibration. So let's look for the natural frequency. We are going to go up with the frequency till we get maximum amplitude of vibrations, and when we go beyond the natural frequency we are going to experience a lower amplitude of vibrations. So let's start going up. We have 7 Hertz, 10, 15, 17, So the natural frequency for the single degree of freedom system is 20 Hertz. Let's see what happens if we are experiencing resonance and I untighten the screw. Let's see what's happening in that case. Yep. So as expected, the same system with two independent masses, it's not going to have the same natural frequency. So the system is not in resonance anymore. The system now it's going to have, because it has two masses, 2 degrees of freedom, it's going to have 2 natural frequencies and 2 modes of vibrations. The 2 natural frequencies are going to be located, one at a lower frequency than the single degree of freedom one, and one at a higher frequency. Let's start looking for the one at a lower rate. I'm going down, 17, 16, 15, yeah, so it's 15.7, and to check out if the masses are in phase or out of phase, we can use or slow motion video or strobe lights. In this case, the two masses are moving in phase. And let's look for the other natural frequency. I'm going up. Remember that it has to be higher than 20. I'm at 21, 23, 24. current natural frequency is at 27, and let's look if the systems, if the masses are in phase or out of phase in this case. Probably you notice that the two masses are moving out of phase in this case. So when the mass is going up, the beam is gonna go down. So again, dynamic absorbers are great to reduce the amplitude of vibrations. Even if we have multiple natural frequencies in those cases, we have more than the single degree of freedom, the amplitude of the vibration is going to be lower. You probably heard a lot of noise in the last natural frequency, but that's due to the frequency, not to the amplitude of the vibrations. Remember that another way to reduce those amplitudes is through damping. We're not demonstrating damping in this case. We are demonstrating using multiple degrees of freedom here. Yeah, thanks a lot.